All right, so the next question, number 4, the curve y is equal to e to the power of 4x tan x has two stationary points. So that's key there, two stationary points. And they are in the interval between 0 and pi over 2. So obtain an expression for dy dx. And also show that your dy dx can be written in the form sec squared x multiplying a plus b sine 2x e to the negative 4x, where a and b are constants, for 4 marks. All right, so now this thing that we are going to differentiate, we have to take note that this is a product, right? So now that it's a product, what it means is derivative of a product, it's v times the derivative of u plus u times the derivative of v. So that's the product aspect of things. Then we also have the trig aspect as well, whereby we should just remember that the derivative of tan is sec squared of x. Then we should also take note of the exponential differentiation. If you are differentiating e to the power of anything, what you should always do is you differentiate the power, you put it there, and then you rewrite your e as it is. So it's like multiplication of e and the derivative of the power. All right, so let's jump onto it. These are the concepts that we are going to be using for this question. So it's a product, as we can see. So this is going to be e. All right, so it's going to be e to the negative 4x multiplied by the derivative of tan x, which is sec squared x, plus tan x multiplied by the derivative of e to the negative 4x. How do we differentiate e to the negative 4x? We differentiate the power, it gives us a negative 4. We rewrite the e as it is, like that. Okay, then we simplify. I am noticing that we can factor out e to the negative 4x. So here we are, e to the negative 4x goes outside, and I now have sec squared x minus 4 tan x. Right, that's the first part, and it hasn't yet shown to what you are looking for right there. Okay, now if we also watch closely on what we are trying to show, there is a sec squared of x that is being factored out. We're supposed to divide by sec squared of x. So let us divide. We are going to end up with e to the negative 4x on the outside. Sec squared x now goes outside. Sec squared into sec squared, we get a 1, minus sec squared into tan x. So now for this one, we are saying that's tan x, which is being divided by sec squared of x, of which we know tan is sine x over cos x, divided by sec squared. We know sec squared, that's 1 over cos squared x. And then this will turn into sine x over cos x multiplied by cos squared over 1. And then cos and cos can cancel. I get my cos x. All right, so our answer is sin x cos x. That's the answer for the division of tan by sec squared. So I'm going to substitute where it belongs. Sin x cos x, sin x cos x. All right, so let's go back and substitute. This becomes 4 sin x cos x. We've managed to factor out sec squared. All right, so if we go back now to what we were doing, you'll find that there is a sine 2x right there. There is a sine of 2x. So for the sine of 2x now, we have to use our identities carefully, because we know that the sine of 2x is identical to 2 sine x cos x. And we have been lucky to have a 4 right there, which we can make use of so that this identity can qualify. So now, if you look at 4 sine x cos x, this could be rewritten as 2 multiplied by 2 sine x cos x, of which we know what 2 sine x cos x stands for. 2 sine x cos x stands for sine of what? 2x. So yes, we can now go back to substitute. So this is going to be e to the negative 4x sec squared x bracket 1 minus 2 sine 2x. So we've managed to get our dy dx in the required format, like that. Right, now let's take a look at part B of the question, which is saying, hence find the exact values of the coordinates of the 2 stationary points. What's a stationary point? It's a point where your derivative is equated to 0. So I'm going to equate my derivative to 0, e to the negative 4x sec squared x 1 minus 2 sine 2x. I'll equate that to 0. So now I solve. When I solve, what's going to happen? Each of these 3 factors shall be equated to 0, and solutions probably could be found. All right, so let's start with the first one. E to the negative 4x is equal to 0. Apply the ln both sides. That's when we'll see that no, this is invalid because we don't have the natural logarithm of 0. So that one is gone. Then we shall also have sec squared of x being equal to 0. So sec squared of x being equal to 0. What identity could we try there? We could try 1 over cos squared. This one is going to give us another invalid as well, because if you attempt to do that, that will be 1 over cos squared is equal to 0, and it will end up being 0 is equal to 1, of which that's false now. That's another invalid result. So now we have to talk about 1 minus 2 sine 2x is equal to 0, which implies the sine of 2x is equal to half. Then we take arcsine of half. So our 2x becomes equal to, that should be pi over 6. Yes, pi over 6. And the other solution in the range for that as well, that would be 150 degrees. Of course, I'm thinking in degrees, but it has to be in radians. 150 degrees was that now in radians. That's going to give us 5 pi over 6 as our second solution. Then we divide each of the solutions by 2, which means now we have pi over 12. Now we have 5 pi over 12 as the other solution. So that's just about it for this question number 4 as well. Then we also take a look at number 6, which is a set of parametric equations. So what we have now is parametric equations of a curve. X is equal to 1 over cos t, y is equal to the natural logarithm of tan t, where t is greater than 0 and t is less than pi over 2. Show that dy dx is equal to cos t over sine squared t. So step number 1, we are going to get dx dt, the derivative for that. So this is a quotient, this is a fraction. For our quotients, just a reminder, if you are differentiating quotients, so if you differentiate quotients, this is going to be v du minus u dv over v squared. That's what we are going to apply for this quotient of x. So let's do that. This is going to be, right, cos t multiplied by the derivative of 1, which is 0, minus 1 times the derivative of cos. Derivative of cos is negative sine t all over the denominator squared. Let me take that again. Sorry. Let me take that again. So all over the square of the denominator, like that. So I'll take that again. Sorry. The square of all over the square of our denominator. Our denominator is now cos squared of t. So in the end, our dx dt will give us a sine of t over cos squared of t. That's dx dt. Then at the same time, we're supposed to find the derivative of y with respect to t. So, right, this is a derivative of ln of a function, and according to the notes, you differentiate the function that is in front of ln, in this case it's an a, over the same function there. So we are going to take the same approach for dy dt. So for our dy dt, this is going to be derivative of tan t, that will be sec squared t, then over tan t. So that's the derivative. Now we just have to play around with the trig identities so that they just give us the resultant that we are looking for. So this is going to be dy dx is equal to dy dt multiplied by dt dx. Let's keep moving. So dy dt is sec squared. Sec squared t, right, over tan t times dt dx. That means we invert our x. Our x becomes cos squared t over sine of t. Right, from there, what happens? We now say sec squared has been known to be 1 over cos squared. And it's being multiplied by cos squared t in the numerator as well. Over, we have a tan t that we know to be a sine over cos. And we also have a sine t here in the denominator. All right, so if we watch closely, 1 over cos squared t multiplied by cos squared t, that's going to give us a 1. And the 1 will all over be the multiplication of these two denominators. And when those two denominators multiply, sine t over cos t multiplied by sine t, I am getting sine squared t over cosine of t. And of course, when one divides a fraction, the fraction becomes inverted and we get cos t over sine squared t. So that's our dy dx. Yes, and we've managed to show perfectly for 5 marks. Part B, find the equation of the tangent of the curve at the point where y is equal to 0. At the point where y is equal to 0. Of course, y is 0, but we don't know what x is. So we need to find the other x coordinate before we do anything. So, if y is 0, what's x? We go back to the parametric, which says y is ln of tangent of t. But we know y is 0, and it's equal to ln of tan t. Let's get the parameter t. That would become, according to laws of logarithms, e to the power of 0 becomes equal to the tangent of t. E to the power of 0 is a 1. So 1 is equal to the tangent of t. Then we take arctan of 1, so our t is a pi over 4. You then take your pi over 4, you substitute that into your x parametric equation. X is 1 over cos t. So our x is now equal to 1 over the cosine of pi over 4. So if we take our calculators to evaluate that, what are we going to get? X is square root of 2. So we now have a pair of coordinates. X is root of 2. I now have to take this off a bit. So my x is the square root of 2 and my y is a 0, which means now I can make progress to find whatever that I'm looking for, because I know my points are x is square root of 2 and my y is a 0. So I want the equation of the tangent. Okay, so now when we talk of a tangent is a straight line. And a straight line is in the form y is equal to mx plus c, where m is the gradient and m, the gradient, comes from dy dx. And our dy dx in this case is a cos t over sine squared t cos t over sine squared t. But we know what parameter t is. Our t was a pi over 4. So we substitute pi over 4. And we get the square root of 2 as our gradient after substituting t is pi over 4 for cos t and sine squared t. So now our equation is y is equal to root 2x plus c. Now to get our c, we substitute. For y, we are going to put a 0. For x, we are going to put a root of 2. So 0 is equal to root of 2 multiplied by the root of 2 plus c, which implies my c is a negative 2. So my equation y is equal to root 2x minus 2.